Now we will discuss example 2.8. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor but has a thickness 3/4 D, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? So in this question, we have the capacitor plates and the dielectric of same area, but the thickness of that dielectric, it is not equal to the gap between the plates. That is the case. So it's given, it's having same area and only 3/4 the separation is the thickness of this dielectric slab. So you in the gap whose that separation is that D, you have 3/4 of that D filled with dielectric and 1/4 is free. That means free space. Okay. And you're asked to find the capacitance, the new capacitance when such a slab is inserted. So it won't be KC0 because it is not completely filling the gap. If it is completely filling the gap, means it becomes K times the previous capacitance. So here anyway with the presence of dielectric, capacitance will be increasing, but by what factor it increases, that we are going to find. So how will we find the new capacitance? You know, the expression for capacitance we can find using the expression C equal to Q by V. So it is this V which we have to find out first. So the thing is this, V will not be same for the two portions. That means 3/4 and 1/4. Suppose the potential difference between the or across the dielectric, suppose we call that potential difference as V1, and in 1/4 of the separation we call the potential difference as V2. So what will be the potential difference between the two plates V? That V will be equal to V1 plus V2. So it's just like a series combination there. So we will have V is equal to V1 plus V2. Now our case is what is V1 and what is V2. So which equation we were using to find V1 and V2? So here V1 is equal to E1 into that distance. What is that distance or separation there? 3/4 into D. Now the question is, what is this E1 there? What is E1? E1 is the electric field in the place where the dielectric is present. You know, the electric field in the presence of dielectric is sigma by K epsilon 0. So sigma by K epsilon 0 is the electric field in the presence of dielectric. That into how much is the distance? 3/4 into D. Okay, so that is our V1. Similarly, what will be V2? V2 equal to E2 into that distance. What is that E2 there? E2 is in the absence of dielectric. So it is sigma by epsilon 0 into what is the distance? 1/4 of D. So 1/4 into D. So these are V1 and V2. So what will be the total potential difference V? That is equal to sigma by K epsilon 0 into 3/4 into D plus sigma by epsilon 0 into 1/4 into D. Now taking the common terms outside, sigma by epsilon 0 into 1/4 into D, within bracket you will have 3 by K plus 1. Here 1 3 is there, here 1 K, so 3 by K, here nothing, that is 1. Okay, so this is the expression for potential difference. Now what we will have, what we want to have is capacitance. Capacitance C is equal to Q by V But what is this Q? Q is the same as sigma A. That is sigma A divided by, here our expression is sigma by epsilon 0 into 1 by 4D into 3 by K plus 1. Just a substitution. Now this sigma and sigma get cancelled and this 4 goes to the numerator, epsilon 0 also goes to the numerator. So substituting in the equation, we have 4 into epsilon 0 A by D into, because sigma get cancelled, into 3 by K plus 1, that is in the denominator. Okay. Then in this equation, epsilon 0 A by D, that is what the capacitance of the capacitor in the absence of dielectric, that we can write as what? C0. So instead of epsilon 0 A by D, I wrote C0 divided by 3 by K plus 1. K I took as common denominator, as means in that denominator. So 3 plus K by K. Now take that K to numerator, 4K C0 by 3K. So this is the answer to that question.